Hello, everyone. Good afternoon. I'm Ping Chen. It's my pleasure to give this presentation on behalf of this paper's authors. So this paper is from Huazhong University of Science and Technology in China. This work is supervised by Professor Yuchong and Professor Feng. Okay. As we know, blob storage, yes, it is widely deployed to store huge amounts of unstructured data, such as photos and documents. Okay, practical blob storage system keep data in different performance storage to make the cost performance trade-off. For example, in Facebook, the new data are first stored in the hot storage to guarantee high access performance. When data become cold, the Facebook moves those data to the warm storages. Okay, we found two interesting things. We found that warm data dominate storage, comprising over 80% at Facebook. And the second one is additionally, most of blobs are small. Okay, in Facebook, almost all photos and 60% of videos are under 1 megabytes. So in storage system, erasure coding provides reliability against failures and is widely deployed. It codes key data blocks into code blocks to form a stripe. Generally, any key of the encoded block in the stripe can recover the data. The figures illustrate a single block repair, where recovering a lost block requires retrieving 2 blocks, leading to high repair cost. So, some techniques to propose to solve this problem. So the regenerating cloud token technology is proposed to solve the high cost problem. Yeah, we know it is repair friendly. This technique splits a large block into smaller sub-blocks, reducing data transfer size. So the number of sub-blocks is called the sub-packetization level. Okay, MSR is one of the efficient approaches to generating codes. It can minimize storage redundancy and are classified into 2 types. The first one is a non-systematic MSR and the systematic MSR. So the former stores only parity blocks, while the later includes both data and the parity blocks. So systematic MSR codes are more popular as they enable direct access to original data with high read performance. So although systematic MSR offers good original data access performance, it performs poorly in repair operations due to accessing multiple sub-blocks, causing lots of non-continuous IOs. So this figure shows the single block repair process. So we can see that a block is divided into many sub-blocks, and repairing a lost block requires the retrieval of multiple sub-blocks in each node. So we confirm this finding through experimentations. So this figure shows the repair performance of different n and key for various blob size. So we can see that the repair performance drops dramatically as the blob size decreases, which demonstrates that the repair performance is limited for small blobs. So to address limitation 1, existing projects use a continuous layout to merge small blobs into equal-sized large blocks to improve the access and I/O efficiency. However, it still causes read amplification due to unnecessary data retrieval. This figure shows that degraded read performance reduces significantly as the merge size increases. Also, the read performance drops dramatically as the block size decreases. So these two phenomena motivate us to do something. Luckily, we found the non-systematic MSR codes perform better for reading small data. It has fewer sub-blocks, resulting in fewer IOs than systematic MSR code. For example, in figure A, we can see that repairing a lost block only requires the retrieval of 3 sub-blocks, while in figure B, the systematic MSR, the clay code in figure B needs to retrieve 6 sub-blocks. So obviously, the technique in figure A is better. So in this paper, we designed NCBlob, which combines key idea from both systematic and non-systematic MSR codes. For small data, we adopt the non-systematic MSR approach, while for large data, we retain the systematic approach. To address some key challenges, we further propose 3 solutions. Okay, first, although non-systematic MSR offers better repair performance, they cause the read amplification when accessing original data, as reading one block requiring decoding key blocks from key nodes. For example, as shown in figure A, if you want to read any byte of original data, you have to decode 2 blocks in the stripe. So while the original data can be directly read out in the figure B, so because it stores the original data block. So therefore, our main goal is to reduce the read amplification for non-systematic MSR. So we find that blob exhibit good access locality. So there are 2 kinds of access locality in blob data, the intra-blob locality and the inter-blob locality. So the former means that small blob is commonly accessed together, such as the photos. So if any byte from such a blob is read, the rest of it should be prefetched. So the inter-blob locality means that there are multiple some blobs that are often accessed together, such as user ID. Some users may be accessed together. So the data locality motivates us to accelerate read performance by encoding data in a group. So for example, considering 2 data block D1 and D2 that have access locality, so we can see that in figure A, without considering the locality, read D1 and D2 need to decode 4 blocks. While in figure B, considering the locality, read D1 and D2 only need to decode 2 blocks. And when D1 is read, D2 has a good chance to be read immediately. So this is the workflow. We designed the split merge encode scheme for improving intra-blob locality, and the merge split encode scheme for improving the inter-blob locality. So the design details are provided in the paper. So secondly, the non-systematic MSR codes effectively repair small blobs, but handling large blobs remain challenging. So observing that clay codes performs well on large blobs. So we propose a hybrid encoding architecture, the non-systematic MSR codes for small blobs and the clay systematic MSR for large blobs. So it's a question, so how to determine the threshold between small and the largest blob? So we select the data size at which disk seek time dominate as the red circle in the figure. So the left one is we denoted the large blob, and the right domain is the small blobs. Okay, we also find that existing non-systematic MSR code only support scenarios where up to 2 blocks are broken. So therefore, we designed the sub-block in rotation, this technology, to support more failure cases. So more details and proof are shown in the paper. So we implement our NCBlob in C++ on Linux. Specifically, we implement a locality manager module to manage the blobs with access locality. So we implement the coding and distribution module based on Ceph and the parallel repair based on the parallel RCE. So our experiments on Alibaba Cloud show that compared with state-of-the-art systematic MSR, NCBlob achieves comparable read throughput, while for the repair performance, NCBlob reduces a single block repair time by up to 45%, and the full node repair time by up to 38%, which demonstrates that the efficiency of our method. So further experiments on NCBlob are presented in the paper. Okay, this is a conclusion. So we have open sourced the code for researchers' convenience. For any technical question, please contact the author's email. Okay, thank you.